Okay, today we're going to be talking about chapter 15.1 and 15.2, which is all about chemical equilibrium. And let's define chemical equilibrium really quickly here. It's going to be when we have opposing reactions traveling at the same rates. And yes, I underlined rates in red. That's really important. We want to have the same rates. It doesn't necessarily mean we're always going to have the same concentrations. We could, but we could not. But the rates are really what's after. And remember, rates we measure from kinetics in typically a molarity per second, sometimes molarity per minute or hour, things like that. So let's give you an example of what we're talking about here with respect to chemical equilibrium. Now, let's say we have a forward reaction, and I'll talk about what I mean by forward reaction in a moment, but we have N2O4, which is a gas, decomposing into 2NO2 gas, and if this reaction is proceeding to the right, we would call this the forward reaction. We would start off with a high concentration of the N2O4 and probably no concentration of the NO2. And as the reaction proceeds, the concentration of N2O4 is going to decrease and the concentration of NO2 is going to increase. We'd call this the forward reaction, and we could write the rate law based on this reaction over here. Rate is equal to K. N2O4, and of course experimentally we'd have to determine the rate law or the order of this reaction. Now, if we take this reaction and we reverse it, we get what was called, obviously, the reverse reaction. So we're taking the product of the forward reaction and we're making it the reactant. And so this reaction is going backwards now. We're going to call it the reverse reaction, and we would say rate is equal to K of NO2. And of course, like I said before, we would have to use experimental data to determine the order of this reaction. So let's jump into it. So when we have the rate of the forward reaction, how fast that forward reaction going is equal to the rate of the reverse reaction, we have what's called an equilibrium. We have equal rates, like we said before, opposite reactions. So we can write an equilibrium like this. And you'll see that the equilibrium is written with a double arrow, meaning the forward reaction, the reaction that's going to the right, is at equal rate with the reaction that's going to the left. Sometimes you might see the arrows written like this, instead of just a double arrow like it is right here. They both mean the same thing. We're at equilibrium. So let's give you an example of what this is all about. Here we have in this picture, we have N2O4 solid, and this is a very cold. This has been cooled down, very cold, and so below the freezing point, or excuse me, below the melting point of N2O4, and you can tell that the N2O4 solid is kind of just a colorless substance, and is probably going to be sitting down here at the bottom somewhere. Now, as we start to warm this reaction up, what's going to happen is we're going to get some N2O4 gas produced, which is also going to be sort of a colorless molecules. But we're also going to start producing some N2 or NO2 gas, and the NO2 gas are these brown molecules here and here. And so you can see in the color of this tube here is becoming a little darker. Once we warm it even further, we're going to get to the point where we get an equilibrium, where we're going to get, as we can see here from this double arrow, an equal rate of how fast N2O4 is becoming NO2 and how fast NO2 is becoming N2O4. And we're even a darker gas here, and there's our NO2 and there is our N2O4. And so we have once those rates are equal, we have established an equilibrium. Okay? Now, equilibrium, we could talk about equilibrium with respect to graphs. And let's say we have, in this graph, we have the concentration of A turning into B. And so at time equals 0 on this graph, which is right here, we've got a very high concentration of A, and we have a very low concentration of B. And we allow this reaction to start proceeding, so we have a decrease in concentration of A here, we have an increase in concentration of B here, and you'll see there becomes a time when these two lines just flatten out. A is not decreasing anymore, B is not increasing anymore, and this point is where we get our equilibrium achieved. Equilibrium is achieved. Okay, and if we're going to take a look at the rate, and of course remember rate is going to be equal to K multiplied by the concentration. Where these two lines are going to meet, the rate, when the rates are equal of forward and reverse reactions, that is where we get our equilibrium. So there's equilibrium occurring right there, and there's an equilibrium occurring right there. So two different graphs kind of talking about the same thing. Okay. Now our next little discussion is going to be about a process called the Haber process. And the Haber process is the process by which nitrogen gas reacts with hydrogen gas to produce ammonia. Now, what scientists found was when they reacted nitrogen and hydrogen, they could only get so much ammonia produced, and there would still be nitrogen and hydrogen present in a reaction vessel. It wouldn't go to completion, and so this is where this idea of equilibrium occurring. And so something that we need to keep in mind, and this is really important, is that equilibrium can be reached from either direction. And so let's talk about what does that mean right here. So in this first graph, we'll call it graph A right here, we have a high concentration of H2, and we have, well, it's not so high, but a lot less of concentration of N2. So there's our H2, and there's our N2. And at time 0, we would say this time equals 0 here. We don't have any NH3. NH3 is represented by that orange line. So the reaction starts, and as this reaction starts, H2's concentration decreases, N2's concentration also decreases, but NH3's concentration does increase. And of course, just like in the previous idea, once those concentrations sort of level out, then we have an equilibrium existing. And this is what researchers found in this Haber process was you could only get so much NH3, and you'd still have some H2 and some N2 present in a reaction vessel. Now, the equilibrium can be reached, like we said, in either direction. And so let's look at this graph B where they're doing the opposite. They're starting with a concentration of NH3 that's, let's say we just inject a vessel with NH3 and we don't have any H2 or N2. And as time goes along, the concentration of NH3 decreases and the concentration of H2 and N2 increases. And again, they get to a point where equilibrium is going to be established or achieved when they all just sort of level back out again. Okay? So let's talk about kind of getting into some of the calculations and the ideas behind this, this equilibrium. So first off, we have an idea called the equilibrium constant expression, and it's also known as the equilibrium expression, and I should have put expression right here. So the equilibrium constant expression is going to be, for concentration, we use the idea of Kc. And K is our equilibrium constant, and C represents concentration. And the way we write equilibrium concentration expressions are, we put the concentration of the products, so in this case here, it's going to be NH3 over N2 H2. Okay? Now, in kinetics, we said we always determined orders and things like that, how we raise things to a power. We talked about it had to be done experimentally, but in equilibrium, we raise each of our concentrations to an exponent that is equal to the coefficients for the balanced equation. So the NH3 has a coefficient of 2, and the H2 has a coefficient of 3, so that's where we're going to raise those to a power for. And so this, what we just wrote here, is called an equilibrium constant expression, and this idea right here of Kc is the equilibrium constant for concentration. Okay? Okay, so now I'm going to give you a sample problem, and if you want to try to do this at home and pause the video and write your equilibrium constant expression for the following reaction that we talked about before, go ahead and pause it now and then press play and see if you get the same thing as I do. Okay? Okay, so if I'm going to write the equilibrium constant expression for this reaction, what I'm going to do is I'm going to put the product over the reactant, and I'm going to raise it to the power equal to the coefficient for the NO2, and that is the equilibrium constant expression, and there we go. Okay, so now let's talk about this equilibrium constant Kc. How do we find the value for this? Because it is going to have a value. Well, we plug in the concentrations when we are at equilibrium of the reactants and products, and we just run the numbers. Again, the C in the Kc represents molarity, it represents concentration. So let's take a look at an example where we do this. It says at equilibrium, the concentration of N2O4 is 0.00140 molar, and NO2 is 0.0172, and that's molar as well there. Calculate the value of the equilibrium constant. So what we're going to do is, again, we're going to use our equilibrium constant expression that we wrote previously, and we're going to plug these values in. And so the value for the N2O4 is going to be 0.00140. And the value for NO2, which is the product, is 0.172, and we're going to raise that to the second power because, again, in the balanced equation, it had a coefficient of 2. Now, when I run that through my calculator, I get an answer of 0.211, and there are going to be no units on equilibrium constants, and we'll talk about why later. And you might be thinking to yourself, what does this number mean? And you'll have to hang with me because I'll talk about what that number means in a different video. It does have an interesting way of looking at it. So let's talk about one other type of K value, and that is a K value called Kp. And Kp is going to be an equilibrium constant for pressure. The expression is written the same way as the Kc expression, but we do have a formula that will allow us to interconvert between Kp and Kc, and here's the formula. And the formula is Kp, which is the equilibrium constant for pressure, is equal to Kc, the equilibrium constant for concentration, multiplied by RT raised to a power of delta N. Now, what delta N is going to be our moles of our gas products minus our moles of our gas reactants. Products minus reactants as we typically deal with delta H values. The R we're going to use is 0.0821 liters atmospheres moles Kelvin, and we're going to use Kelvin temperature to plug this value in. So here's an example. We'll go back to the Haber process again, and it says we have 1N2 plus 3H2 yields 2NH3. We'll say this reaction's at equilibrium. The Kc value has been calculated previously as 9.6 at 300 degrees Celsius. Calculate Kp for this temperature. So what we're going to do to convert between these two is, again, we're given Kc, we want to calculate Kp. So Kp is going to equal Kc RT delta N. So we're just going to plug some values in. Again, Kc 9.60 multiplied by 0.0821 multiplied by our temperature, which was 300 C. We're going to have to add 273 to that to get 573, and we're going to raise it to the value of delta N. Now, in this, remember, delta N is going to be products of gas minus reactants of gas, and so we have two moles of products minus a total of, there's 3 there and there's 1 there, minus 4, and so delta N is going to equal -2. And so let's go ahead and plug that in as a -2 there, raised to the -2 power. And so run this through my calculator and see what we get here. Okay, so the answer that I get here, I get 4.34, that is 4, times 10 to the negative third is equal to Kp. And I'm going to leave units off there because we don't use units for K values. Okay, so that's how we calculate or write equilibrium constant expressions, and that's how we convert between Kp and Kc. And hope you have a great weekend.